Hello, everyone. Thank you for joining us for another live webinar session hosted by E-Tech and All About Circuits. My name is Jeff Child, and I'll be your moderator. Today's session is brought to you by Siglent Technologies and is titled Understanding How Performance Oscilloscope Designs Impacts High-Fidelity Applications, Visualization, and Analysis. Let me tell you about our presenter today. Chris Armstrong is the Director of Marketing at Siglent Technologies. Chris brings more than 22 years of experience in test and measurement, from sensitive measurement applications to multi-purpose benchtop test, to integrating complete systems controlling instrumentation across a number of platforms. Chris has obtained a Bachelor of Science in Computer Science and Engineering from the University of Toledo and an MBA from Case Western Reserve University. Following this presentation, we'll have a live Q&A with Chris, and you can submit your questions during this session using the chat box that you see on the right-hand side of your screen. We will provide you, our attendees, with a downloadable copy of the presentation once the session is complete, and this will be available on the Resources tab, along with a few other links that you can access at any time during the presentation. Thank you, everyone, for joining, and with that, I'll hand it off to Chris to get us started. Welcome, Chris.
Thanks, Jeff. Appreciate it. Well, hopefully you can all see and hear me perfectly well. As Jeff said, I'm Chris Armstrong, here from Siglent Technologies. Today, I have the pleasure of talking with you about some exciting updates and changes taking place in oscilloscopes as the industry continues to move to higher resolution and higher performance instruments. We're going to talk through some different parts of instrumentation design and how that impacts the measurements that engineers need to make every day. So we're really going to discuss this in 4 different phases. We're going to start with some key specifications, how we understand them and how they interact, then dig a little deeper into design quality, choices we make at the design level that don't always show up in the first page of a data sheet, but have an important impact on our measurement fidelity. Third, we'll look at some capabilities added to the instrument that impact how signals are visualized on the display. We'll touch on analysis impacts as well, more about data, statistics, and measurements than visual debugging. And we'll conclude today with how all these elements work together in key applications, looking at a series of use cases that benefit from all the careful design work that brings signal fidelity to life in these newest high-performance oscilloscopes. All right, so let's start by talking about some of these key specifications. When comparing between oscilloscopes or determining their value in a given application, these are the top specifications that often come up: sampling rate, resolution, memory depth, and the combination of bandwidth and filtering. These 4 specs actually work together in a number of ways that create different trade-offs and capabilities for a number of applications. So let's take a look at what each mean and how they interact in common use cases. First, sampling rate. So we'll touch a little bit here, but I think everyone probably knows what we mean by sampling rate. So sampling rate, sampling precision, they affect analysis, measurements on time and frequency. It's about time between individual points that are ultimately posted to the display. We tend to measure this in gigasamples per second, or sometimes megasamples per second. So that's how many points go by in a total 1-second period. The importance of this is especially true for frequency measurements, like we would make with an FFT. One downside here is that higher frequency sampling will capture and display higher bandwidth noise. It's also true of higher actual bandwidth. A higher bandwidth scope with the same sampling could alias on high bandwidth noise, creating some noise artifacts for us. So what sampling do we typically see in a high resolution, high performance scope? So there are 10 and 12-bit oscilloscopes on the market today, ranging all the way from a gigasample and a quarter, up to 20 gigasamples or more. So what you have to look out for is scopes that don't have sort of 2.5 times the frequency sampling for the bandwidth of your signals. This can cause aliasing and misrepresentation of some of these higher speed signals. Beyond that, as we'll see through this discussion, having extra oversampling capability can be very important to signal analysis because it allows the engineer flexibility in bandwidth and filtering to optimize their signal fidelity. So with that in mind, let's look at what is changing within each sample as we move to a higher resolution platform. So with resolution, there are lots of different ways to talk about resolution and filtering averaging. So these are all really interrelated. So companies talk about these in slightly different ways. What's most important to start with is true resolution. So true resolution is equivalent to the number of bits captured by the A to D for each sample. Additional bits of resolution are often discussed as part of an ENOB or part of a result of filtering, but we need to start with the true resolution of that A to D. Looking at that A to D and that true resolution, the quantization error is the voltage difference between consecutive values on the A to D itself. Each additional bit drops the quantization error in half. So everything else being equal, a 12-bit A to D has quantization error 1/16 of an 8-bit A to D. As we will see, though, everything else being equal doesn't really result in the precision measurements you might want or need. So from a specification perspective, the quantization is typically rolled into an offset error for a given channel range. So now that we have these samples coming out of our scope with more information in each sample, how does that work with the rest of our sort of key specifications? So this is an important discussion here about the combinations and trade-offs of memory, bandwidth, and filtering. So these work with sample rate and resolution to create both opportunities and trade-offs. First, memory and sampling work together to bound the longest time that can be captured with maximum sampling and bandwidth by the scope. For instance, an oscilloscope like the SDS7000A from Siglent with up to 1 billion points of memory can capture a channel at 20 gigasamples for 50 milliseconds in total. So this means that on a scope like that, you can set the horizontal range to as long as 5 milliseconds per division while still fully capturing the 4 gigahertz signal. This is useful for slow developing signals or rare signal artifacts in time. You can then zoom in millions of times to view the fast signal artifacts in context of the larger signal. Most applications, though, even for performance scopes, don't require max bandwidth for most measurements. This is where the memory can be used flexibly and purposed specifically to an application. So we'll talk a little bit about memory-focused application spaces later. But here, we can use filtering techniques to trade memory, sample rate, and bandwidth for increased signal fidelity. And this can often be expressed as increased resolution. So the vast majority of applications really fall into this middle ground, where maximized signal fidelity is the goal. We can utilize the memory and the sample rate in exchange. This is effectively a type of boxcar filtering, where combining consecutive samples and groups allows us to artificially reduce the quantization error by estimating voltage levels between the actual bits. So these trade-offs create opportunities to improve and optimize noise and ultimately signal fidelity within a smaller bandwidth. Using this method effectively reduces the bandwidth along with the sampling reduction. So the ability to optimize here is dramatically reduced if the scope starts out short on memory or sample rate. Some high-resolution scopes don't have enough filtering options at all and don't include those because they don't have enough memory or sampling rate to make them worthwhile. So let's see how this really affects noise and signal fidelity and what combinations of capabilities we should expect to see from a high-performance scope. So here is an example of the filtering options available on an oscilloscope like the 7000. Exceptionally deep memory here means that even when consuming a number of samples to generate a filtered data point, the instrument can still capture long enough events for debug and analysis. So we see here on this slide, we're talking about using it in a 1 or 2 channel mode with 20 gigasamples per second, up to 4 gigahertz. Because of the memory and the sample rate capabilities, we have a number of different, we call them iris modes here, averaging modes, where we can include, improve the resolution, the resolution of the signal by changing the way that sampling is configured. And consequently, the noise and the bandwidth change. So you can get reductions in noise at the expense trade-off of bandwidth. So we can see here, even as these samples are consumed by the filtering, right? You're losing bandwidth because we're consuming these samples. The effective bandwidth required for many of these applications, we can still be maintained. So with an instrument like this, an engineer can choose between 16-bit precision and 34 megahertz down at the bottom, all the way up to 200 or 220 microvolts RMS noise with a full bandwidth of 4 gigahertz. So in this chart here, total bit representation or total bit resolution is a representation of how much the filtering reduces the quantization error. It's not a true number of bits anymore, but so make sure to understand the trade-offs and requirements for the memory and the sampling rate. As a starting point, this means understanding the total time you need to capture, the maximum bandwidth you need to be visible, and the amount of noise that's acceptable in your application. For instance, needing to capture longer time periods will limit your sample rate once the memory gets full. Reducing these sample rate effects, the bandwidth, and then the filtering modes that are available. So keep a lookout here for scopes without filtering modes. Really, they're leaving precision on the table. The flexibility given to the engineers here with this trade-off is an important one. This way, one scope with sufficient bandwidth can clearly help you visualize a variety of signals across the spectrum. Without it, noise can become a larger issue in many application spaces. So let's look at a few screenshots here of various configurations to help us understand the nuances of filtering and bandwidth. So first, we're going to focus on the top left. This is a pretty familiar sort of standard 8-bit scope capture, showing some noise on some relatively small signals here. Depending on the nature of the characterization or debugging you're doing, this might be fine, right? But more precise analysis might be required for these signals, especially if their use is in lower bandwidth systems, requiring more accurate levels and signal aspects. And let's move down to the bottom left. So to combat some of that noise, we can invest in a 12-bit oscilloscope here at the bottom left. In many ways, you can see this investment pays off immediately. Clearly, not only has the resolution been improved, but the actual noise has been significantly reduced. Now, this is due to design improvements in addition to the bit change. So now with lower noise, we can clearly see some ringing, especially on the fast edges of the top signal in each chart. Because the 12-bit scope is still at full bandwidth, these artifacts aren't attenuated. So you can still see that those ringing and those edges. Now let's move over to the right. As we look over here, we see we've added some of the filtering capabilities. So clearly, great way to remove some of the noise. But we can see that it's also attenuated some of those ringing effects and those high-frequency artifacts, as you'd expect. So the real question is for your application, do you want to see that? Or is that unimportant because of the bandwidth of the actual receiver to these signals? So with a combination of tools like this, engineers can optimize noise as well as visual and analytical representation of the signals. So let's go further in depth on what I meant when I said there were design improvements to the 12-bit scope beyond just the actual change in resolution when we went from the top left to the bottom left. And so what I really meant there is that there are design fundamentals that need to be considered when you're changing design, in addition to just swapping out an A to D. So these are several kind of quality elements that are critical to a solid design. We're going to take a look at each and how they impact different measurements that we might want to make. For this discussion, we're going to focus on key quality design elements of noise, gain accuracy, and isolation. These are really some of the most important considerations that we find for improving signal fidelity. At the end, we'll also discuss ENOB, so effective number of bits. What ENOB stands for is sort of an industry standard representation of overall precision that encompasses a lot of these kind of chief design choices made. In this way, it can be a useful benchmark for overall design. So actual noise performance is our first key quality metric here. It's important that this is specified or measured at full bandwidth and sampling rate, so you get kind of a core noise performance metric for an oscilloscope. So look out for scopes that don't provide any noise level data or don't specify it properly. So without the detail here to reference, analysis features as well as modes like filtering can quickly become sort of impractical or useless. So one important note here is that high frequency noise is a significant contributor to overall noise. So less expensive scopes with naturally lower bandwidth will typically show less noise. It's another reason why filtering capabilities can be useful and important. They can extend an oscilloscope's value to a wider set of lower bandwidth applications. So core noise performance at sample rate and max bandwidth should be achievable across any kind of configuration. And then we can use modes here to improve the noise for the specific use case. So here we're looking at our table of experimental data for the 7000 series again. We see how that noise is impacted by filtering modes. But it's worth noting that many scopes, like this, also have channel-independent hardware bandwidth filters. So the 7000A has a customizable channel bandwidth limit. From these data points down in the bottom right chart, you can see that the channel filter can further improve the noise beyond just the effective bandwidth filtering. So in fact, there we have our 2.5-bit Iris mode and 200 megahertz bandwidth value is lower than the next step down at 140 megahertz bandwidth using just the filtering mode. So that's at least partially because the hardware bandwidth filter does a better job of limiting, attenuating that high frequency noise. So this is experimental data and can depend on the nature of this noise encountered. But in general, this tool set allows an engineer to optimize noise even further on a per channel basis, whereas the software filtering mode is typically common to all channels. So important to be able to isolate different channels and get the most out of each signal. So when designing an oscilloscope, noise can come from many sources. Most important here are component selection and layout. They have large impact on noise. Also, noise is strongly impacted here by design, outside of that main analog front end. So EMI considerations, power cleanliness make an impact. Important thing to remember is designing a high performance oscilloscope goes well beyond just adding a new A to D with extra bits to your existing design. The best designs consider both key specifications as they relate to use cases, as well as overall design quality. And that starts with noise. So another important kind of quality design element is gain accuracy. So gain accuracy is expressed as a percentage. This is really a voltage error on your A to D that's proportional to the voltage that's being put in. So this is more tightly controlled by the A to D linearity and the component selection in the front end. So gain accuracy affects our measurements in a couple of different ways. First, we'll see later how scale offset capabilities on a range can empower additional measurement capabilities. Improved gain error is often a necessity before extending those offset scales. But since these values are typically sort of 3% is less, as we see on the chart here, of a signal, and tend to operate more as an offset than noise, they would typically not be as important in visual applications. For instance, many scope applications are focused on changes and signal artifacts in time more than whether the line on the display is 3 millivolts too high or 3 millivolts too low. But as we move to more analytic measurements, characterizing RF and high-speed signals and comparing these signals statistically, the differences from channel to channel can become more important to be debugging and failure analysis applications. So here on this chart here, we see a comparison between two different levels of oscilloscopes, sort of a mid-range and a higher performance oscilloscope, sort of headlined by the SDS 2000X HD, and then the 7000 series Siglent on the second level. So here we're talking really about how these two different sort of levels of oscilloscope capability and their gain accuracy, especially on these higher ranges. So on the right, you see a statistical analysis of channel ranges and gain errors on our instrument and how they fit well within that sort of specification band. So you typically have a tighter band for higher ranges, and then often a little looser band as you get down towards the true noise level of the instrument. So we'll depend on this accuracy to correctly analyze signals, especially when we need to stretch the capability of our ranges and resolution to capture signal artifacts. So let's go to our sort of third design element here and talk for a moment about isolation. So isolation is really often expressed as a ratio. This is about the error injected to our signal from adjacent channel signal path, other signals going into the oscilloscope. So this is most largely in a design related to layout, part quality, and some EMI sort of design considerations. It can be important to look out for oscilloscopes that have surprisingly low isolation, as this may leave them susceptible to other coupling or noise sources as well. So as an example here, let's take the SDS 2000X HD, which has channel isolation specified at 60 dBc. So you can see from the calculation there, this is really equivalent to 1,000 to 1 ratio. So there are other high resolution oscilloscopes available that have much lower isolation, as low as 100 to 1 or even less at high frequency. So this 10x difference in isolation is important in many high resolution experiments where small signal artifacts kind of are commonly analyzed with larger signals as well in order to determine causality or do different levels of debugging. So as we'll see here in a minute, this can have a surprising kind of outsized effect on some important signal fidelity applications. So ENOB really is a known expression of this sort of overall accuracy. It's not always specified. It's often typical, and it can vary by measurement method as well. But changes in ENOB can be a good barometer for overall system design quality improvements. Actual quantization error is usually a small contribution. So just taking an 8-bit scope, changing it to 12 bits will not have a meaningful impact on ENOB. So here, just a quick look at a few different scopes and how they compare. Right, some high-resolution oscilloscopes will have an ENOB closer to an 8-bit scope than one of our high-resolution scopes. And really, this is all about these other design considerations that we've talked about. So it's important to understand sort of that precision of an instrument in your use case and how best to accurately make your measurements. So with all that in mind, I want to take a second just to understand that simple noise expressions are often used as a shorthand for precision and accuracy. While noise is important, you have to dig deeper, I think, to understand the true precision in a given application for your oscilloscope. So gain, isolation, these noise, all are important factors. So you may require extensive memory, sampling, filtering techniques as well. So in the end, make sure to evaluate your measurement requirements, building up from the noise floor as a starting point and not using that as an endpoint. So let's look at one way to visually compare and contrast these different error sources and techniques. So when we talk about visual testing with an oscilloscope, one way to look at this is with pixels on a display. An oscilloscope display is specified in inches and pixels. And while pixel pitch can differ, I find it useful to consider the interplay here between error sources in terms of number of pixels and uncertainty. Here are some kind of example-based calculations of where error is coming from. All these errors converted to units of pixels visualized on the display. So some core assumptions are made and simplified, but I think the results show an interesting relationship. Quantization error, as we discussed, is quite small. Even an 8-bit scope with 16 times the quantization error has a very small overall impact in terms of pixels on the display. So just going to that 12-bit really doesn't have an impact. You need to be able to add vertical zoom capability to get any use out of it, and we'll see how that impacts actual signals. So noise is obviously more impactful on small signals and realistic errors of 1 LSB, and in some ways 1 pixel when you're looking at these higher signal levels. We can see gain error here estimated as a percentage of pixels, or the error at the top of the display. We estimate this really as an error at the top of the display with the ground at the bottom. So let's kind of compare these two scopes. So scope 2 is a competitive 12-bit scope, really in the same price range as the SDS 2000X HD. So in the first example here, small signal level, the noise and gain performance reduces the overall error to about half the other scope. With the higher level signals, the gain error becomes really the dominant error, thanks to Siglent's tighter 0.5% gain accuracy on this range. So worth noting here that when we add the isolation, we add another signal into this mix, can be a major issue when looking especially at the smaller signals. So without good isolation, that impact from adjacent channels can really dwarf all the other errors within the system. Typically on your higher level signals, it's not as big of a problem. So also important to remember kind of visually how these errors manifest. Noise will fill those pixels with samples, whereas gain would typically just create uncertainty in the correct values, but not visual noise. So it's important to make sure an oscilloscope is actually fully rendering waveforms to the pixel level. So it's possible some scopes added a larger display with more resolution, but that doesn't mean they updated the waveform processing engine underneath to the larger pixel array. So make sure they're mapping correctly to really optimize the viewing experience. So with this comparison as our background, let's look at some important capabilities that we add into our oscilloscopes that make a big impact on how you visualize and debug signals with your scope. So we have three main visual impacts here: vertical zoom, scale offset, and FFTs, or how we convert that data into the frequency domain. So let's dig in. So without a zoom functionality, high res is almost all wasted with a normal display and live readings. Now, as we see, the quantization error is often already at the pixel level. So zoom is required to really see between those pixels. You can store, capture, and change the scale, but live debugging is really critical to signal analysis and learning. In addition to a powerful vertical zoom, a scope like the 7000 can have channel-independent zoom windows, allowing for simple visual orientation of complex signals. So let's take a look at how that vertical zoom works. So we start with the long capture on the left in a sort of a signal sequence out on the order of a millisecond per division. We need deep memory to get our high sample rate, so we can zoom in horizontally to get the right image. This you can do with almost any scope with the right amount of memory. With the combination of low noise at bandwidth and deeper memory and sampling, we can zoom in even further until we start to see a hint of a signal anomaly in the middle there. Now we can really attack it by going from that display on the left to zoom in on vertically. So now we've zoomed in vertically and we can see a series of pulses there invading our signal. So we can capture this and ultimately be able to correlate and determine the cause. So here, even though I've zoomed in horizontally 10,000 times, we still have enough sampling overhead to utilize a filtering mode to clean this signal. So I chose a 1.5 bit additional iris bits here to get the best view. So to summarize that, we're really, this is the area we've zoomed in on, that little gray box in the other signal. So that silver rectangle there is the blown up area on the bottom of the screen. So just like memory and sampling rate allow us overhead to zoom in on the horizontal, excellent noise, isolation, and resolution allow us to zoom in vertically as well. Then we can use features like persistence mode and history to visualize the signal changes over time. Like there I captured a persistence in the mode capture in the top right. So scale offset is also an important factor here. So these wider offset capabilities are important because they allow engineers to get more out of the high resolution by using a smaller range to actually capture their signals. This reduces the actual quantization noise and improves the zoom functionality. So as an example here, visualizing a signal that is 100 millivolts in amplitude riding on top of a 25 volt signal. On the Siglent, you can use the 200 millivolt range. On some other scopes, you might be forced to go up to nearly the 2.8 volt per division setting. So that same 12 bits of resolution are now spread over 14 times the voltage. So that almost eliminates the 16x improvement from going to the 12-bit A to D in the first place. So this is an important factor that allows you to really get the most out of those bits. Without it, a lot of those are wasted on scale choices. So you like to think about things like, what's the best range you can use for your signal? How does that optimize the resolution? How can you visualize it using zoom functions available? So offset range can be an important factor to overlook when you're selecting an oscilloscope. And then third, FFT quality, FFT visualization. So a little bit different than ranging and zoom. FFTs allow us to visualize the frequency components of a signal a little differently. So the FFT's accuracy is largely dependent on the number of points of resolution of each point. So as FFT depth increases, the effective RBW is reduced, creating more frequency points closer together, giving you a more accurate representation in the RF domain. So in this example here, the 7000 uses memory to enable up to 32 million points, 12-bit data in a single FFT visualization. So you can set up a 100 megahertz span, which is 4 million points, that has a 386 hertz RBW, or you can go out to the full 32 million points here at a 1 gigahertz span, and that allows you to produce signals with 482 hertz RBW and a sample rate of 10 gigasamples. So across a whole 1 gigahertz span on the display, you can have frequency points that are just less than 300 hertz apart. So we combine this with markers, peak readings, and scaling tools to capture signals equivalent to a wideband real-time spectrum analysis look you can correlate now with your other time domain signals. As you might expect, the isolation we talked about before is critical in these applications, since the RF signals are especially good at creating noise on adjacent channels. So a quick stop here. Wanted to talk about analysis as we move from visualization tools into analysis with just memory. So there are tools like sequence mode, history, search and navigation that are really just about taking the memory, folding it in different ways to create statistical and visualization tools. Not as dependent on high resolution, so we won't focus on them here. But this includes things like jitter and eye diagram measurements on high performance scopes, where memory and sample rate become sort of the critical values, and help you visualize and analyze signals in different ways, with or without high resolution capabilities. So we're going to finish up here today with sort of 4 key applications that highlight the critical elements of an oscilloscope for high resolution capabilities. So signal on signal, an important use case, especially for visualization capabilities, including vertical zoom. We'll talk about mixed signal debugging, how that adds FFT analysis into the equation, power analysis, which requires some precise measurements, including harmonics and phase. And then lastly, frequency analysis or Bode plots, which highlight a couple other analysis requirements in the RF domain. So let's look at how each of these benefits from the design qualities, specifications, and capabilities we learned about. So crosstalk and related debugging deals with how signals and circuits are interrelated, often related to layout and emission issues. Now, these can be difficult to kind of capture and analyze. So, once we can do that, we can use the vertical zoom to get the best look at these kind of signals. So we're going to take a look at a video here in a minute, and this video shows you a capture process on a difficult to visualize signal riding on another signal. So we start by kind of optimizing the range and offset of the pink signal here, so we can trigger on the anomaly. Then, once we get that kind of positioned, we're going to zoom in horizontally and vertically until we have a top of that pulse period spread out. So positioning that, now we're going to start to zoom in horizontally. Now we can use persistence to sort of, once we isolate that top of that wave there, we're going to spread out a little bit further. There we go. Now we're zoomed in good. So now we can switch to the persistence mode to isolate sort of an infrequent pulse event here. There we go. So there we see that pulse that's happening within our signal. So noise, isolation, and resolution are really all key to this, but scale, offset, vertical zoom capabilities are actually what allow you to find this small pattern that is really hidden behind the overshoot level on this signal. So hopefully we notice kind of how that combination of capabilities really makes that difficult to capture anomaly pretty straightforward. So now let's look at some mixed signal debugging. So mixed domain. So high bandwidth scopes can be used a lot for this sort of RF and mixed domain testing. This includes RF signals, whether unwanted emissions or purposeful modulations. So measuring these together is an important application, and signal quality really becomes top of mind here. So flexibility in your configuration is really critical to be able to optimize memory bandwidth and FFT depth here. So let's see how we can measure kind of signals and get the best visualization capabilities in an application like this. So as an example, IoT debugging requires advanced tools like this because they're cross-domain signals and tight layouts. Functional testing of these interactions between signals like this serial data stream on the bottom and the FSK signal on the top requires high fidelity. So are bugs being created by transmission timing events, emissions, layout issues? The only way to really solve that is capturing live, correlated, high-fidelity signals across that small IoT device, both on the RF and inter-chip area, is often the best sort of debugging methodology. So that brings us to power quality. Power quality applications are really common in your mainstream oscilloscopes today. So Siglent's tools include a full set of measurements, shown on the right here. So harmonics, safe operating area, ripple effects, and a number of others. So critical to accurate analysis of these signals is really the small differences between those current and voltage waveforms. So being able to accurately make phase difference measurements requires oversampling and low noise. Isolation is often important here because you have multiple signals of different levels, and the FFT capability is important because of your harmonics analysis. So filtering can be especially useful here since power analysis is often conducted at lower frequencies, and noise is certainly an issue. So small variance in an amplitude between these channels has an impact on your analysis. Consider gain accuracy across channels as you determine sort of best instrument for your power analysis measurements. So power analysis often requires current and sometimes differential probe solutions. So let's look briefly at our last application, which requires a generator channel actually to conduct the characterization. And that's really Bode plot and frequency analysis work. So it's a special mode where we analyze gain and phase across frequency, where we're typically talking about the input and output of an RF device and doing comparisons in that way. So like power analysis, you have small phase and amplitude errors here that have a big effect on overall measurement. The scaling and gain capabilities here can simplify the automation because this is typically done with a sweeping generator in the background. So being able to control the sweep and quickly and easily automatically configure the scope for those measurements is important. So often this is used at low frequencies with an oscilloscope, characterized devices below 20 or 50 megahertz. So with an instrument like the 7000 though, and the ability to control an external generator, you can easily go up to 120 megahertz in frequency analysis while maintaining excellent phase and gain accuracy. And that's really due to the control capabilities and the advanced sample rate. So these applications overall highlight several key areas where high resolution within the context of a properly designed scope, excellent visual and analysis capabilities can take engineers further, faster into their debugging and problem solving. It rarely comes down to just resolution, but requires careful design and implementation across an entire system for capturing and visualizing this kind of data. Siglent's a leader in these design considerations, providing new analysis capabilities that will shape these applications for the future. That sort of brings us to our summary at the end here, right? We want to consider, we talked about key specifications, design quality elements, visualization, analysis, and capabilities. So as you're looking at high resolution oscilloscopes and trying to decide how they work for you, how they're going to work in your application, questions you can ask yourself, like, do you really need more resolution, accuracy, or precision? Which one? What's the best range you're going to be able to use for your signal? How does that optimize the useful resolution? How can you visualize it using zoom functions available? And what will that signal really look like with noise, isolation, and gain errors? Is there enough memory and oversampling to improve that data further with filtering? And how will all that kind of information go together to present itself on the display? So it's all about really trying to get the most out of your oscilloscope capabilities and finding the right one for your application. So we have to, when considering that, look out for those design quality corners being cut. I wouldn't consider any specification in a vacuum. I consider kind of a complete solution, make sure it's built around a modern platform from the ground up with these concerns in mind. And that's how you can get a great tool for your application and your requirements. Which really brings us to the end. Thanks so much.
Chris, thank you for that great presentation. I know I personally learned quite a bit. In particular, those side-by-side comparisons really were interesting, I thought. Okay, so we already have several good questions from our audience. I'd like to remind everyone that now is the time to submit your questions if you have them for Chris, so we can get them queued up there. First question is kind of maybe it's a oscilloscope adjacent kind of question, but he asks, what's the fastest Sigma Delta ADC these days? That's an interesting question.
That is a great question. And actually that takes me back to days at Keithley.
Right.
Do that more on more precision instruments. So I guess the answer is I have no idea what the fastest ones available today are.
Yeah, I used to cover them years ago, and they keep going faster. So
certainly they keep going faster, and they have more resolution.
Yeah,
more bits of resolution, but also better noise capabilities as well. So right. I think that's and today many companies in this space are designing their own A to Ds and their own silicon for the front end applications here. So that's an important aspect of this sort of design.
And that's why you need these advanced scopes, right, Chris? Because
that's true too, right? These tools can be important for testing some of those capabilities.
Yeah. Our next question is, about high resolution, when to use it and when not. Do I need a high resolution oscilloscope for all my measurements?
Yeah, I think this whole process here is that we've gone through today is sort of that important consideration, right? Certainly, you don't always need it, right? I'd also say there are really very few advantages to a scope, just like the one you have that happens to have more bits to it, right? It's this whole process, this combination of visual capabilities and tools, design quality improvements on the back end, and the underlying specifications that all work together to make a scope great for a particular application or a particular need. So I kind of like to go through this process and think to myself when I'm trying to make a test about, what do I need? What do I need in time? What do I need in bandwidth? What do I want that signal to look like on the display when I'm capturing it? How do I have to go through that process? And I think when you go through that process, you learn a lot both about your application and about the tool set. And that allows you to, I think, marry the two in the best appropriate way.
Gotcha. Yeah, as you said, there's so many considerations. This next question is, what's the most important consideration for high resolution measurements?
Yeah, I think as I work through it, I think for most applications, the visualization tools become most important, right? It's pretty easy to compare the top level specs. Even most of the noise specs are reasonably easy to find, right? But your actual success in easily debugging signals and digging in and finding root cause has a lot more to do, I think, with the visualization tools and sort of that finishing touch, right? So, if you will, the last mile of that design is connecting the engineer to to that technology that's built into the scope, and the way we do that really is through a combination of visual tools highlighted around vertical zoom and noise capabilities.
Got it. Next, I love it when these questions get very specific. This one's pretty specific. My measurements rely more on data archival and analysis than what you see on a scope display. How can I find the information on an instrument that's most important for my needs?
Yeah, I think that's the flip side of the visual set. I think it's important, right? Especially as you get towards more high performance oscilloscopes, you're capturing more data, you're doing statistical analysis to really evaluate different kinds of parts and products, right? And so important there to understand all those error states that we talked about, right? So what error impact your gain measurements, your gain, your offset, your noise, your isolation really have, and be able to really clearly understand sort of those error bars in not just the visualization, not just what it looks like on the screen, but the actual errors in that can be present in that data, so that you can more correctly do that analysis. So I think a great way to kind of work through this process and work down from specs, work down from noise into those details can help you understand your application and the tools that are available to you.
Got it. Next question is about cost. I know that years ago, scopes used to be so expensive, like the VP of engineering would have to make decisions. But I know there's different ranges. The question is, when comparing instruments, how should I consider cost versus other capabilities?
Yeah, I think this is obviously it's an important trade-off for everyone, right? So I try to think about the use case, the application requirement to start with. Go through part of this process that we did, and then you could find a set of tools or a number of scopes that will meet that need, right? And you can compare them from a value perspective. And then I think the important thing to then think about is the flexibility that you might need going forward, right? So the things we tend to pay for in an oscilloscope are memory, sampling rate, bandwidth, the top level specifications. The big jumps there are where the cost typically comes in, right? So I think consider your application, consider how your needs may change over the next few years, and then look at how bandwidth and memory can impact sort of the filtering capabilities and your total ability to use that scope in different configurations and modes. So I like to start by looking at what I need today, finding options, and then deciding how much I'm willing to pay for certain flexibility moving forward, kind of protection for future usage.
Gotcha. And as you say, you have to consider the future as well, you were saying, yeah. Another very specific question. Do some Siglent oscilloscopes have an option to trigger on a particular sequence of pulses, which can be specified in the trigger settings? The example, like the Xilinx Vivado integrated scope can do this, he says.
Yeah, so there's certainly a lot of trigger modes. We didn't talk much about trigger modes today. A little different topic, but a lot of trigger modes and sequences of pulses, runs, different pulse configurations is a common trigger mode in a lot of these oscilloscopes. So yeah, I think worthy of a totally different presentation. All the different ways to trigger and capture that data.
Yeah, that's a whole different subject, isn't it?
But an important one too, right? So an important consideration, for your on your test and your application, how you need to trigger is another important consideration.
Our next question has to do with precision. What are the most important capabilities if I need high precision, but if I do most of my debugging using the display?
Yeah, so I think maybe a subtly different kind of version of stuff we've talked about, right? So I think the important thing to remember is that when you're talking about precision and precision and visual debugging, right? Just remember how that map works, right? The precision is subtly different than accuracy, right? Do you need clean signals without noise? Do you need to absolutely know what the voltage level is at a given point, and what error can you stand to have in that signal, right? So, I think going through this process that we did today, looking at different capabilities within an instrument and different needs in your application, can kind of help you kind of go through that process. But I think whenever you're talking about visual debugging, I think you'll find that some of those visual concerns like zoom and scaling capabilities really become important to how you ultimately use the instrument, how it goes together, and how quickly and easily you can actually make tests and take measurements.
Got it. Well, Chris, it looks like we've answered all the questions that have come in so far. We're going to wait a couple of minutes to see if more come in. But Chris, while we're waiting, any sort of takeaways or things you want to elaborate on while we're waiting?
No, I think I am all talked out, Jeff. Appreciate your guys' time today, and for anyone who stopped by, you can always reach us at Siglent with more questions.
Yeah, that's great. So, Chris, thank you for that great presentation, and thank you all for all your questions. So, in just a moment, we're going to redirect you to Siglent's hub page on All About Circuits, and there you'll be able to view the session on demand whenever you want, along with other Siglent resources that are available. So with that, thank you for your time, and we look forward to seeing all of you in another live session sometime soon. Thank you.
Thanks so much.